Hello and welcome to our Wednesday webinar from the IEA Clean Coal Center. My name is Benedicta and I'm the Communications Officer here. Our monthly webinars are based on our technical reports, which are available from our website, www.iea-coal.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration. Any questions to this webinar, please feel free to send them in as we go along and we'll answer them at the end of the webinar. The subject for today's webinar is Current Technologies for Co-firing Biomass with Coal, presented by Xing Zhang. The report on this topic will be published in June, and I'll now hand you on to Xing.
Hello, good afternoon. This webinar is based on my current report. It covers the following areas: co-firing different biomass fuels, biomass pretreatment, combustion-related issues for co-firing operating issues, and its impacts on environmental controls. Finally, the conclusion. Co-firing has been most evident in Europe for the last 20 years or so, but it is now in decline with some countries phasing out of coal policies. However, the Netherlands still supports co-firing at full coal-fired power plants through its SDE Plus scheme, although the country is considering coal phasing out by 2030. In Eastern Europe, there's some co-firing. For example, Bulgaria has 2 power plants and a full CHP plant co-firing with 10 to 30% of biomass. Bosnia also co-fires its lignite. Meanwhile, co-firing in Asia is expanding fast. At IEA-CCC, we have studied co-firing for many years and published reports on various aspects of this subject. My study is an update for the previous report. The major types of biomass fuels for co-firing with coal are wood, grass, and straw-based. Imported wood pellets are the main biomass co-fired in Europe. In Denmark, a large amount of local straw has been used. Japan and South Korea mainly coal-fired imported wood pellets, although Japan also coal-fires wasted wood. In China and India, agriculture waste is the main fuel. This is a win-win as it reduces the local pollution from burning crop residues as well as reducing CO2 emissions from coal-fired power plants. This figure shows heating values and steam temperature of various biomass. We can see agriculture residues have low steam temperature and heating value, hence it is more challenging for co-firing. Also, wood chips and pellets, especially pretreated ones, have similar characteristics and more uniform than crop residues, therefore have less impact on the power plant. For residues like straw, deposition and corrosion issues are more of a problem, so specific strategies are needed for high ratio co-firing. For example, IFK at University of Stuttgart recommended a straw issue of less than 25% for minimum impact on boiler. They also suggested to use online probe for monitoring conditions in the boiler. Much effort has gone into developing efficient and cost-effective biomass pretreatment technologies to improve the physical and chemical properties and the energy density of biomass. Common pretreatment technologies include washing and leaching, steam explosion, torrefaction, wet torrefaction, and densification. Leaching or washing the biomass with rainwater, tap water, or acidic or alkaline solutions is an effective way to remove troublesome elements. Bioleaching has attracted attention recently. Laboratory results show it is more efficient than water for removing most contaminants except sodium. Steam explosion has been widely used in the production of bioethanol. It is now being used to pretreat biomass for power generation. Pellets from steam explosion are easier to mill in large coal mills, which minimize retrofitting cost at a coal-fired power plant. Research has also been carried out on various feedstocks such as rice straw, corn stover, or coffee husks. Walmart took the steam explosion technology to the pilot scale with its BioTrack system, as shown in the photo on the right. Wet torrefaction technology came after dry torrefaction and is also known as hydrothermal carbonization. Laboratory research is active in this area. A pilot scale test was conducted at the Technical University of Munich in January 2018. Result hasn't been published yet from the test. Densification, a proven technology. Commercial products are available for it. Torrefaction is currently the most active area in biomass pretreatment. It is a popular research topic in the last 2 decades. The figure here shows that torrefied biomass has many improved properties compared to raw biomass. Several companies are trying to commercialize torrefaction technology. The initiation of commercializing took off in 2010 to 2011, and quite a few plants were planned. There were 65 companies working on biomass torrefaction globally in 2017, and many of these are still in operation. Even so, the deployment of torrefaction technology has not been fulfilled as fast as originally expected. Steady industry production and the commercial status have not yet been established, although torrefied biomass is widely available in the market. Many reactor concepts have been considered for biomass torrefaction. Here's a collection of torrefaction reactors available in the commercial market, which have been deployed at torrefaction plants. The rotary drum reactor is the proven technology. Tall Group built a torrefaction plant with an indirectly heated rotary drum reactor in Belgium. The plant has a production capacity of 4 tons per year and is still in commercial operation. The American company Teosils can also produce 2 tons per year torrefied biomass at a sugar mill and is building a bigger capacity plant with rotary drum reactor. The National Renewable Energy Center of Spain has also built a pilot plant to torrefy herbaceous biomass, such as cereal straw. School conveyor reactor has also been commercialized. A Swedish company built a plant in 2012 with an annual capacity of 16,000 ton black pellets and has signed an agreement in September 2019 to build another plant in China. To maximize the benefit of biomass pretreatment, the 2 or more technologies are often combined. For example, ECN in the Netherlands has developed and patented TOWash, which combines washing and torrefaction to improve low-grade biomass feedstock. torrefaction can be integrated with pelletization, referred as a TOP. Now we move on to coal combust biomass and coal. Coal-firing technologies are commonly classified into three types: direct coal-firing, indirect coal-firing, and parallel coal-firing, as illustrated here. Direct coal-firing in powerized coal boilers has dominated coal-firing for the last 20 years, so the technology is developed and mature. The photo on the left is Uniper's 1.1 gigawatt MPP3 coal-fired power plant in the Netherlands. This is a new ultra-supercritical power plant with a design efficiency of 47% and coal-fired 15% biomass. Fluidized bed boiler is most suitable for coal firing. Existing coal-fired FBCs can be easily adapted to coal firing. In general, FBC boilers can substitute a higher level of coal with biomass and handle biomass with higher moisture content and a larger particle size than PC boilers. They can achieve a high efficiency, typically over 90%, even with challenging low-grade fuels. FBC coal-firing can reduce the amount of ash discharge and the limestone consumption. One problem with FBC, though, is the increased likelihood of bed agglomeration occurring. There's a lot of research on coal-firing different biomass with FBC system. For example, the figure on the right is the design of a pilot 750 kilowatts circulating FBC system for coal-firing pine chips with Turkish lignite. Recent research also combined oxy-fuel combustion or CFD modeling with CFB technology. There are 46 FBC coal-firing units greater than 50 megawatts in the world. 43 are in operation and 3 are planned. The Legnica power plant in Poland is the world's first and the largest supercritical coal-firing CFB in operation at up to 10% biomass. The world's largest ultra-supercritical FBC power plant is Kospos Green Power Plant with 2 1,000 megawatt units in South Korea. In Japan, the under construction Kusyu power plant has been designed to coal-fire 30% biomass in a CFB boiler. The commonly known indirect coal-firing technology is coupling a biomass gasifier with a coal boiler. There are many advantages to this setup, but it has not been widely adapted in Europe, largely due to the expense. There are fewer than 10 coal gas-firing power plants, but all have closed with the decline of coal use in Europe. Only Armer 9 in the Netherlands is still in operation. The bottom photo is Armer 9, which coal-fired up to 50% biomass, but only 5% is indirectly coal-fired with 29 megawatts FBC gas-fire. However, coal gasification is a popular choice in China as it is easy to measure the amount of biomass consumed. The first pilot test was carried out in 2013 at Guodian Jinmen power plant with 10.8 megawatts gas-fire. The top photo is Unit 6 of Xiangyang Power Station. This supercritical power plant has a 10.8 megawatts fluidized bed gas-fire, which became operational in September 2018. The middle photo is the Datang Changshan 600 megawatts supercritical unit with 20 megawatts FB gas-fired. It started operation just last December. Optimizing the ratio of biomass to coal for coal-firing has always been a goal. Drax in the UK tried various coal-firing ratios before converting its unit to 100% biomass. Armour-9 coal-fired 50% wood pellets last year and plans to move to 80% this year. This figure shows the coal-firing ratio for 40 coal-firing units in Japan. 31 of them coal-fires less than 3% biomass, is shown in the blue column. 8 units are coal-firing above 3%, with 5 above 20%. But many Japanese companies have been working on how to increase the coal-firing ratio. For example, Nokia coal-fired power plant began coal-firing 5% wood pellets in Unit 1 in 2015 and increased the ratio to 30% for Unit 2 in 2016. And IHI modified the mill to powerize biomass at a power plant belongs to Nippon Steel and achieved a 25% biomass coal-firing ratio in 2017. In the test launched in January 2018 at the Suma Energy Park power plant, a ratio of 34% at rated load and 50% at partial load were achieved. Oxy-fuel combustion as a part of a carbon capture system can be combined with coal-firing to maximize CO2 reduction. This diagram is a recent pilot scale trial to coal-fire coal and cereal biomass in a retrofitted 100 kilowatt powerized fuel combustor. The test result showed that experience gained from air firing can be readily applied to oxy-firing systems. Ash deposition was similar in both air and oxy-firing, indicating that similar approaches to handling falling and corrosion can be used in both cases. The European Commission's BioOxySORB project published a report in 2018. This demonstration program included oxy-fuel coal-firing research at the lab and a pilot scale at the AFK at the University of Stuttgart. Large-scale tests were carried out in a 20 megawatts facility by Cadent in Spain. A first guideline in Europe was developed for biomass coal combustion under oxy-fuel conditions. Concerns about retrofitting, such as biomass coal milling, are also discussed. Coal-firing coal and biomass in oxy-fuel fluidized bed has been considered as one of the most promising technologies for capturing CO2. Academic studies have been active in this area in the past decade. Some bench-scale and pilot-scale experiment has been carried out. Some results claim that oxy-fuel combustion with coal and biomass coal-firing in a CFB boiler can even reduce CO2 emissions by 120%. Pressurized oxy combustion is the focus for future. Oxy-fuel combustion has the drawbacks of cost of retrofitting and energy efficiency penalties due to the higher compression and the pressure drop loss from oxy-fuel process. Despite pretreatment of biomass and whatever combustion method and the biomass ratios are used, coal-firing biomass has impacts on coal-fired power plants, on the combustion, operating logistics, and environmental control systems, as summarized in this slide. I'll start from operating issues. There are 3 different routes for milling. They can be cold milled, or they can be milled separately and combined at the burner, or they can be even milled separately and burned separately. When milling for coal firing, especially in coal milling route, biomass ratio must be considered, generally up to 20% of biomass. Fuel grindability, mass balance, and heat balance are also need to be considered. Low-Share Energy System Limited is the market leader in design and supply of mills. Their key product is a vertical roller mill. The burners may require modification. This example is Unit 3 of Stootstrap CHP plant. The coal mill and burner were modified in 2017 to prevent the load decreasing. Additional flame scanner were installed to solve the flame detection problem. Minor changes were made to the existing ignition system to enable continuous operation at low load. The oil ignitor has been replaced by a plasma van. Oil nozzles have been replaced by smaller ones. Another example is this Unit 3 of USC Nordland plant. The issue here was that coal forms an airtight seal in the silo, but processed pellets don't. So dust can flow from the pulverizer to feeder and eventually block it. To prevent this, a rotary valve has been installed. A biomass flame is slightly different from coal flame. Adjustment of flame scanner was sufficient to ensure safe operation of pulverizer. Computational fluid dynamic modeling is an efficient tool to enhance understanding of coal-firing combustion issues and problems. CFD can provide information over the entire domain of the furnace, especially in the region where measurements are difficult or almost impossible to obtain. Another advantage of CFD is that it gives the flexibility to change parameters and input values easily. As the figure shown here, coal-firing CFD models consist of gas phase submodels, particle phase submodels, and additional models which focus on NOx emissions and ash-related problems. These models are available for air and oxy-fuel conditions. The recent trend is modeling oxy-fuel coal-firing and CFB modeling in 3D. State-of-art CFD-based models can solve the complex interdependent processes like fluid flow, turbulence, heat transfer, and heterogeneous and homogeneous chemical reactions involved in coal combustion. However, the complete description of particle trajectory, chemistry of devolatilization, char oxidation, volatile combustion is still mainly based on simple models. To ensure the simulation is adequately completed, CFD model need to be validated with experimental data. One of the main concerns of coal-firing is the high alkali content of biomass, which causes problems with the ash. Ash deposition during coal-firing is more complicated than for coal combustion. The figure here shows formation processes of the main ash-related issues. The alkali and alkaline earth metals reacted with other inorganic non-metallic components to produce deposit. The common ones include silicates, chlorides, and sulfate of potassium and calcium. These compounds are more concentrated in agricultural waste than wood pellets. The deposit led to slugging in combustors, falling of heat transfer surfaces, and bed agglomeration in flue gas bed combustors. Ash deposition is also affected by physical properties. To reduce slugging and falling, as mentioned earlier, CFD modeling can help understanding of ash deposition. Alkali carbonates can be used as a solvent to reduce hydrogen chloride. Combustion additives such as choline can be used to change the ash composition and further reduce the presence of volatile alkali species. Fortunately, the potassium chloride and the sulfate components of biomass are mainly water soluble. Washing and leaching with tap water can reduce them directly. Thermal pretreatment such as torrefaction have also proved effective. Coal-firing herbaceous biomass with low falling tendency coal such as lignite reduces slugging in PC boilers and slugging and bed agglomeration in FBC boilers. Falling can be controlled by the use of online cleaning systems. Some biomass, such agricultural waste, have high alkali and or chlorine content, or both. Coal-firing them, particularly straw or switchgrass, can exhibit a corrosion problem. Chlorine in combustion gases, especially at high temperatures, can accelerate the corrosion of combustion systems and the flue gas cleaning systems. The same corrosion prevention method that's used in boiler can be used elsewhere, such as modification of the reheater, superheater, in order to allow larger spacing, more soot blowing, and lowering the live steam temperature to below 500 degrees, and so on. Other ways to minimize corrosion include the use of more corrosion-resistant high high corrosion-resistant alloyed materials such as Sanicro 25 and 28. Chromium-based or nickel-based diffusion coating can be applied for protection. Slugging, agglomeration, and corrosion occur together, and so these issues should be investigated jointly rather than separately. The risk of fire and explosion are an important issue for biomass coal-firing. Biomass has a low ignition temperature and high reactivity, making it harder to handle than coal. Torrefied wood is more brittle than untreated biomass, giving it a greater chance of exploding. The factors affecting explosion include particle fineness, a high reactivity of dust materials, a high concentration concentration of dust in air, low ignition temperature of dust particles, proximity to a high energy ignition source, and a favorable oxidizing environment. This this actually is a short video shows the explosion test conducted by JIXCON. Apart from CO2 reduction, coal firing can bring a positive emission reduction from a coal-fired power plant. Most biomass fuels have a lower ash content than coal, so in general, coal firing reduces the total amount of fly ash produced. But in some cases, an increase or non-change in the amount of PM has been measured. The effect depends on the type of biomass and the performance of PM collection equipment. Fly ash particles from biomass combustion tend to be significantly smaller than coal fly ash. The capture efficiency of ESPs tends to decrease with an increasing coal-firing ratio. With coal-firing biomass, SO2 emissions invariably decrease, often in proportion to the amount of biomass coal-fired. NOx emissions are harder to predict and vary with the biomass used and the manner in which the nitrogen is released. However, there's evidence that coal firing can deactivate SCR catalysts. This due to alkali constituents in biomass poisoning the vanadium-based catalyst in SCR systems. Some strategies have been established to reduce poisoning of catalyst. As mentioned, there's an overall reduction in fly ash production from coal firing power plant compared to coal plant. The ash contents from different biomass and coal differ in composition. This creates a burden for utilizing the fly ash from coal firing, especially at high coal firing ratio. On a worldwide level, no or a limited number of guidelines with best practice have been developed in ash management. This table lists biomass ash application and requirements based on a survey conducted by IEA Task 32. To summarize, coal-firing biomass has been practiced in Europe for more than 20 years. Some of the technologies are commercially mature. Agriculture waste are more commonly used in Asia, which reduce local air pollution. But high alkali content can cause more issues with slugging, falling, and corrosion. Methods to prevent and reduce these drawbacks are being developed. Biomass pretreatment is often used. Some pretreatment technologies are in or close to commercial operation but can be expensive. Overall energy efficiency should be considered when choosing a pretreatment method. Biomass handling requires care due to the risk of fire and explosion. Direct coal-firing of biomass in large PC coal-fired power plant is still the most popular choice, although FBC boiler is more suitable for coal-firing. Coal gasification coal-firing is the main method in China. Oxy-fuel coal-firing with biomass has the potential to reduce CO2 emissions dramatically. Progress continues to be made to facilitate coal-firing biomass with coal, but it comes at a cost, hence requires governmental support. Thank you for listening. Now, let's see if there's any questions regarding my webinar today. Okay, the first one is from Hugh Lee. What checks can be done and are being done to ensure that particularly biomass is carbon neutral? Right. This question is actually, I think, related to biomass sustainability. Our center has done a report, especially on this topic, and a webinar was also done on this topic. But my understanding is when we utilize biomass, I mean, apart from agriculture and forestry waste, when they use wood pellet, they ensure it comes from the source. The sustainability has been enforced. My understanding is there's guidelines and perhaps even law has been established in this area. But to fully understand this question, I would like to refer you to our report, which I believe was published last year. The second question is from Barry. Can you comment on biomass co-firing in USA? The United States has a vast resource of forestry, and the coal fleet in America is quite old. In my opinion, is co-firing is economic solution to retrofit the aged coal-fired power plant and consequently extend the plant's life. However, coal-firing activities is not very active in the United States. Perhaps the gas price is relatively cheap in America. I hope I have understand your question. Another question is from Eureka. How has plant efficiency changed when biomass co-firing has been implemented? Generally speaking, adding co-firing systems to a coal-fired power plant, decrease the plant efficiency. Also, biomass fuel efficiency is not as high as coal, so overall it reduced the plant efficiency slightly. But for a lot of coal-firing practice, they actually retrofit the old coal-fired power plant. So when retrofit a coal-fired power plant to coal-fire biomass, this actually can increase the plant efficiency. a comment from my colleague Michael Wild. Sorry, the question is flooding in before I read it. It's gone up. Just wanted to comment that there's many more torrefaction plants in operation or construction currently, for instance, but not complete. FETRA 150 kilometers and the national carbon and net fuel Baldwin, yeah, Michael included quite a long list of coal-fired torrefaction power plant. It's actually in my report, I did include quite a lot of more torrefaction plant. In my report, I classified the torrefaction technologies by the reactor used in the torrefaction plant. So for more information, I would like to recommend you to read my report, which will be published shortly. There's another comment from Sebastian. Thank you. Plant efficiency is not modified since the exhaust gas temperature doesn't change. However, depowering is probable as a biomass has less LHV. So this might answer the question Erica proposed earlier. There's another question from Johnson. Is there much ongoing research for the use of torrefaction gas? Well, to be honest, I'm not quite sure, as this is out of the remit of my report. My report is focusing on coal-firing technology. It covers the whole spectrum of coal-firing, torrefaction, and also our report focus on coal. Torrefaction, I touched it in my report, but not in too detailed, too deepened technical details. Sorry, is it time? Oh, sorry, I think time is up.
Thank you so much. That's all we have time for. Only to say that the slides from the webinar are available to download from the webinar page of our website very soon. And the next webinar from us will be on the 15th of April at 12 o'clock as usual. And that will be on CCUS status, barriers and potential, presented by Greg Kelsall. Thank you all, and thank you for joining us today. Goodbye.